Hello everyone. Today we will discuss the different types of memory that exist on a GPU, create one and initialize data, and finally look into powerful abstractions that helps us do complex things very easily. As you see on the screen here, there are four types of memory within a GPU. There is a private memory accessible only by a thread. There is a shared memory where all the threads within a block can use. There is a global memory where all the threads across all the blocks can use. And finally, we have a read-only or a cache memory, which is used to store certain parameters. Depending on which memory you end up using for your program will determine the efficiency of the program. And we will look into those in further videos. Today, we will create a simple global memory. Look, see how we can initialize data, and finally we'll print them on the screen. So I'll go ahead and import certain libraries that we need. I'll go and I'll initialize a few variables. So here I'm saying I want data type of int32. I'll end up creating 4 blocks and threads down below. Since there are 4 blocks and 4 threads, there is a total of 16 elements that I can create and assign it to each thread. And as we've done before in the prior videos, first step in any GPU program within Mojo is to get the context or a logical reference to the GPU, which is initiated by calling device context. Then we'll use the create buffer function to create the global memory. Since I wanted 16 elements because I will be creating 16 threads, so that's the amount of global memory I'll end up creating. Once you create the global memory with create buffer, it will be initialized to 0. To make it little more interesting, we will write some values to it from 0 to 15 so as to just have some values initialized on the global memory apart from other than 0. So we'll make use of what's called as map to host. What it does is it gives access to CPU, and what does CPU do? It uses a function called iota and initializes values from 0 to max size, which is in this case 16. So it will put all the values from 0 to 15 on these memory locations that we ended up creating. So now when we go back and check the buffer that we created, we see that it has values initialized. Again, this is in a real world program, you will have your data elements that you will be initializing on this memory. But here, for the sake of initializing values other than 0, we make use of certain built-in functions to write data to GPU. Now, when it comes to memory layout, one of the two most popular options you have is one is called row major, where you arrange elements in memory in a row format, which is to be read from left to right. So in this case, you read it from 0, 1, 2, 3 from left to right, and you shift to the second row, which is from 4 to 7 and so on. Remember, we created 4 blocks and 4 threads within each block. So hence the 4x4 layout, and a row major for such a layout would look something like this. If it's a column major, then you arrange the elements from top to bottom when you read it. So here the value 0 goes here, but then 1, 2, 3. So you go column wise first, and then you increase the values. So 0, 1, 2, 3, 4, 5, 6, 7. So a single row would read something like 0, 4, 8, 12. Now, how you arrange elements within the memory sometimes will determine again the speed in which you execute the program. There are certain algorithms which will depend on certain arrangement of memory, and knowing these options exist will help you better refine your algorithms. Now, So you can arrange the locations or arrange the data within a memory yourself by accessing the device buffer. But Mojo and Max platform gives you a very powerful abstraction called LayoutTensor. In this, you can use the LayoutTensor abstraction to arrange elements automatically using row or column measure without you manually doing it yourself. So you can think of it as a very convenient wrapper that will help you do powerful things and save things, especially when it comes to memory, as opposed to you tapping into the buffer directly. The abstraction or the layout tensor does not own the memory. The device buffer still owns the memory, but you get very convenient APIs to manipulate them. And there are 3 steps in using the abstraction. First is you define your style. So in this case, I have 4 blocks and 4 threads, and I choose to use row major as an example. So I define the style saying layout row major 4x4. Then I define what's called as a type, a tensor type. So using the style and the data type I initialized above, which is int32, I define the type. The third step is to create an instance of that type. So, it is very analogous to, let's say you create a class first and then you create an instance of a class. Very similarly, you create an input tensor type with this layout style. And then finally, you create a sample tensor. Note that I've used the same buffer, the device buffer that was created and initialized from elements 0 to 15. So essentially, this sample tensor is a wrapper around the device buffer that we created earlier. So in any GPU, similar to a GPU program we wrote earlier, I'll write a function which is also called as a kernel. I'll queue the function. The prerequisites to queue the function is to provide the number of blocks and threads, in this case 4x4. I also pass an input tensor which we created here, which is then accepted here as itensor, and the kernel does very basic thing, which is to print the block, the thread, and the values within the tensor. Finally, we call the synchronize function, which essentially waits for all the threads to finish their function and then print them on the screen. You see here, there is block 1, which has 4 threads printing 4, 5, 6, 7. The first block printing 0, 1, 2, 3. Now, we have 16 elements and we chose 4x4 as our layout style. You can always choose any style that you have depending on the program you're writing. It could be 8x2 or 2x8 in this case. Since we have 16 elements, the best practice or the convention is to use 1 thread for each data element. So as long as you have 16 threads and 16 data elements, the style can be anything you choose. So 4x4 was a convenient way, but you can always choose 8x2 or 2x8, whichever you prefer. So we just change that ever so slightly and then run the exact same program. And you see the output is pretty similar, except now each block has 2 threads and has 2 elements within each block, 0 and 1 in this case, and the block 1 has 2 and 3. You can further just enhance your kernel. Instead of simply printing, you can add a multiplier and multiply it with a constant. Here we chose 2 as our constant, just to ever so slightly increase the complexity of the kernel. And then instead of now, the only major difference from the earlier kernel is we just do the work here, but the printing is now is done below here as a way of using the map to host function, which gives some flexibility for CPU to print the way it wants to. So now you'll see here, you queue the function, you multiply, use the multiply kernel, and all it does is just multiplies the elements in your tensor. But instead of directly printing here, we go back to the CPU, we use the layout style. In this case, it's 4x4. In this case, it's 8x2. and cleverly print elements in a 2D array format in both cases. In this case, it's a 4x4 print. In this case, it's a 8x2 print. So again, slightly enhancing our simple example to show you that the layout tensor not only helps us providing inputs to the kernel, but you can also tap into the output so that any downstream activities can also take advantage of this abstraction. So hope you learned about memory and the abstractions that are available within Mojo, and in further videos we'll see how we can tap into these APIs to better design our kernels. Thank you very much. I'll see you in the next video.